Section 7.6 Metals, Nonmetals, and Metalloids. Atomic radii, ionization energies, and electron affinities are properties of individual atoms. With the exception of the noble gases, however, none of the elements exist in nature as individual atoms. To get a broader understanding of the properties of elements, we must also examine the periodic trends in properties that involve large collections of atoms. The elements can be broadly grouped into categories of metals, nonmetals, and metalloids. The classification is shown in Figure 7.15. Figure 7.15, metals, metalloids, and nonmetals. The majority of elements are metals. Metallic character increases from right to left across a period and also increases from top to bottom in a group. Roughly 3/4 of the elements are metals, situated in the left and middle portions of the table. The nonmetals are at the right corner, and the metalloids are between the metals and the nonmetals. Hydrogen, which is located at the top left corner, is a nonmetal. This is why we set off hydrogen from the remaining group 1A elements in Figure 7.15 by inserting a space between hydrogen box and the lithium box. Some of the distinguishing properties of metals and nonmetals are summarized in Table 7.3. Table 7.3. Metals have a shiny luster, various colors, although most are silvery. Solids are malleable and ductile, good conductors of heat and electricity, and most metal oxides are ionic solids that are basic. Nonmetals don't have a luster, various colors. Solids are usually brittle, some are hard, some are soft, poor conductors of heat and electricity. Most nonmetal oxides are molecular substances that form acidic solutions, tend to form anions or oxyanions in aqueous solution. The more an element exhibits a physical and chemical properties of metals, the greater its metallic character. As indicated in 7.15, metallic character generally increases as we proceed down a column of the periodic table and increases as we proceed from right to left in a row. Now let's examine the close relationship that exists between electron configurations and the properties of metal, nonmetals, and metalloids. Metals. Most metallic elements exhibit the shiny luster that we associate with metals. Metals conduct heat and electricity. In general, they're malleable, which means they can be pounded into sheets, and ductile can be drawn into wires. All are solids at room temperature except for mercury. The two metals melt slightly above temperature, cesium at 28 and gallium at 29.8. At the other extreme, many metals melt at very high temperatures. For example, chromium melts at 1900 Celsius. Metals tend to have low ionization energies, therefore they tend to form positive ions relatively easily. As a result, metals are oxidized. They lose electrons when they undergo chemical reactions. The fact is illustrated in 7.17, where the first ionization energies of metals, nonmetals, and metalloids are compared. Among the fundamental atomic properties, radius, electron configuration, electron affinity, and so forth, the first ionization energy is the best indicator of whether an element will behave as a metal or a nonmetal. The relative ease of oxidation of common metals was discussed earlier in section 4.4. As we noted there, many metals are oxidized by a variety of common substances, including oxygen and acids. Figure 7.17. A comparison of the first ionization energies of metals versus nonmetals. Values of the first ionization energies for metals are markedly lower than those of nonmetals. The red circles correspond to metallic elements, the blue squares to nonmetals, and the black triangles to metalloids. The dashed line at 925 kilojoules per mole separates the metals from the nonmetals. Figure 7.18 shows the oxidation states for some representative ions of both metals and nonmetals. As we noted in section 2.7, the charge of any alkaline metal is always positive 1, and that of any alkaline earth metal is always positive 2 in their compounds. From atoms belonging to either of these groups, the outer s electrons are easily lost, yielding a noble gas configuration. For metals belonging to groups with partially occupied p orbitals, groups 3a through 7a, the observed cations are formed either by losing only the outer p electrons, such as 10-2, or the outer s and p, such as 10-4. The charge on transition metals does not follow in the obvious pattern. One of the characteristic features of the transition metals is their ability to form more than one positive ion. For example, iron may be +2 in some compounds, +3 in others. Compounds of metals with nonmetals tend to be ionic substances. For example, most metal oxides and halides are ionic solids. To illustrate the reaction between nickel metal and oxygen produces nickel oxide, an ionic solid containing nickel 2+ and oxygen 2- ions. The oxides are particularly important because of the great abundance of oxygen in our environment. Most metal oxides are basic. Those that dissolve in water react to form metal hydroxides, as in the following examples. A metal oxide plus a water yields a metal hydroxide. The basicity of metal oxides is due to the oxide ion, which reacts with water according to the net equation. Oxygen plus water yields hydroxide. Metal oxides also demonstrate their basicity by reacting with acids to form salt plus water. A metal oxide plus an acid yields salt plus a water. In contrast, we'll soon see that nonmetal oxides are acidic, dissolving in water to form acidic compounds and reacting with bases to form salts. Nonmetals. Nonmetals vary greatly in appearance. They're not lustrous and generally are poor conductors of heat and electricity. Their melting points are generally lower than those of the metals, although diamond, a form of carbon, melts at 3570 Celsius. Under ordinary conditions, 7 nonmetals exist diametric molecules. 5 of these are gases: hydrogen, nitrogen, oxygen, fluorine, and chlorine. 1 is a liquid, bromine, and 1 is a volatile solid, iodine. Excluding the noble gases, the remaining nonmetals are solids that can either be hard, such as diamond, or soft, such as sulfur. Because of their electron affinities, nonmetals tend to gain electrons when they react with metals. For example, the reaction of aluminum with bromine produces aluminum bromide, an ionic compound containing aluminum ion 3+ and bromide ion 1-. A nonmetal typically will gain enough electrons to fill its outermost occupied p subshell, giving a noble gas electron configuration. For example, the bromine atom gains 1 electron to fill a 4p subshell. Compounds composed entirely of nonmetals are typically molecular substances. For example, the oxides, halides, and hydrides of the nonmetals are molecular substances that tend to be gases, liquids, or low melting point solids at room temperature. Most nonmetal oxides are acidic. Those that dissolve in water react to form acids, as in the following examples. Carbon dioxide plus water yields carbonic acid. The reaction of carbon dioxide with water accounts for the acidity of carbonated water and to some extent rainwater. Because sulfur is present in oil and coal, combustion of these common fuels produces sulfur dioxide and sulfur trioxide. These substances dissolve in water to produce acid rain, a major pollution problem in many parts of the world. Like acids, most nonmetal oxides dissolve in basic solutions to form a salt plus water. A nonmetal oxide plus a base yields a salt plus water. Figure 721, the reaction of carbon dioxide with water. The water has been made slightly basic and contains a few drops of bromothymol blue, an acid-base indicator that's blue in basic solution. Upon the addition of a piece of solid carbon dioxide, CO2, the color changes to yellow, indicating an acidic solution. The mist is due to the water droplets condensed from the air by the solid carbon dioxide gas. Metalloids. Metalloids have properties intermediate of those metals and those of nonmetals. They may have some characteristic metallic properties but lack others. For example, silicon looks like a metal, but is brittle rather than malleable and is a much poorer conductor of heat and electricity than metals. Compounds of metalloids can have characteristics of the compounds of metals or nonmetals depending on the specific compound. Several of the metalloids, most notably silicon, are electrical semiconductors and are principal elements used in the manufacture of integrated circuits and computer chips. One of the reasons metalloids such as silicon be used for integrated circuits is the fact that their electrical conductivity is intermediate between that of the metals and nonmetals. Very pure silicon is an electrical insulator, but its conductivity can be dramatically increased with the addition of specific impurities, dopants. This modification provides a mechanism for controlling the electrical conductivity by controlling its chemical composition. We'll return to this point in Chapter 12.